So let's discuss atomic theory. So we're going to talk about the 5 models: solid sphere, plum pudding, nuclear, planetary, and quantum model. So this is how the atomic model has actually evolved over the years. It all started with John Dalton. So John Dalton was actually a British chemist, and he proposed that atoms actually exist like solid spheres. And he said these cannot be broken down and they're made up of the same material. Then came J.J. Thomson, who was also an English physicist, and he said it's more like a plum pudding, right? So the entire pudding is positively charged, and you have, the raisins in the plum pudding. So he said the raisins are like electrons. The electrons are negatively charged. And so he is credited, he's always given credit for the discovery of electrons. And Rutherford basically proposed that there is a nucleus in the center of the atom, right? And that is positively charged. And you have electrons around it. Niels Bohr developed it on his idea, and he said the atomic model is more like a planetary model. So this is what you see in schools, right? The Bohr's model that you draw in school. And so he said the electrons basically orbited around the nucleus, and it looked like the solar planet, right? And so they exist in quantized energy levels. However, this was also not agreed upon entirely, and then the model that we agree upon now as scientists is called Schrödinger's model. So Schrödinger was an Austrian physicist who was obsessed with his cat. But apart from that, he made a lot of contributions to the quantum model and to quantum mechanics in general. So he proposed that the electrons actually exist in orbitals. So they're like cloud-like structures around the nucleus. And you can't actually determine the speed and the position of the electron at the same time. And he said it's more like a wave-like pattern. So this is what is called, you might have heard, dual nature of matter or dual nature of electrons. So that is what is credited to Schrödinger. So the next thing we want to talk about are subatomic particles. So there are about 3 subatomic particles. And if you were to pass them through a positive and a negatively charged plates, you would see a deflection, right? So the electrons being negatively charged, because it's negatively charged, they will get deflected towards the positively charged plate, right? Because unlike charges attract, remember? And because protons are positively charged, they would get deflected towards the negatively charged plate. And neutrons, because they have no charge, will basically pass through. So let's discuss atomic theory. So we're going to talk about the 5 models: solid sphere, plum pudding, nuclear, planetary, and quantum model. So this is how the atomic model has actually evolved over the years. It all started with John Dalton. So John Dalton was actually a British chemist, and he proposed that atoms actually exist like solid spheres. And he said these cannot be broken down and they're made up of the same material. Then came J.J. Thomson, who was also an English physicist, and he said it's more like a plum pudding, right? So the entire pudding is positively charged, and you have, the raisins in the plum pudding. So he said the raisins are like electrons. The electrons are negatively charged. And so he is credited, he's always given credit for the discovery of electrons. So there are different groups and even blocks of the periodic table, right? The first one is group 1. So we have, the first one is called group 1. The hydrogen is not part of group 1, right? So this is group 1. They're also called alkali metals. Yeah. So they're called alkali metals. Group 2 are called alkaline earth metals. Then we have another name that I expect you to know, and these are group 7, and they are called halogens. Now, I know you might be thinking that it says this is 17, right? So why did I call it group 7? So I want you to think about groups in this way. So say this is group 1. Again, I said this even before. Hydrogen is not part of group 1. This is group 2. This is 3. So you skip over the numbering. So the transition elements, these are the transition metals, right? You skip them when you think about numbering, and you say 3, 4, 5, 6, and 7. And this is 8. These are noble gases. Group 8 is noble gases. They do not react, right? So we have group 1, 2, and 3. So up to group 3, up till here, everything is metallic. So we have metals. Yeah? Hydrogen is not a metal. Then group 4 onwards, group 4 to 7, we have non-metals. So the majority of the periodic table is in fact metallic. And then we have these guys in the middle here. You know, you see this green block? These weirdos here in green. So they are called metalloids, right? They are called metalloids. Now, metalloids, what's special about them is they can have both kind of properties. So they have some metallic and some non-metallic properties. And they can be made to behave either way. Like silicon, for example, which is a very important metalloid. And it is significant for our computer industry or technology in general. So silicon chips, right? So silicon chips function the way they do is because it's a metalloid. So it can conduct electricity when you want it to, and it cannot conduct electricity when you don't want it to. Okay. Another thing I want you to remember is groups. So when we're talking about groups, most of these groups elements in one group would have similar properties. So that's something you need to remember. So elements in a certain group will have similar properties. So when we move on to the next chapter, I will explain more about the electronic structure and how are the electrons arranged in atoms and things like that. The next thing we want to discuss is subatomic particles. The next thing we want to discuss is their charges and their mass, right? So protons have a charge of +1, whereas electrons have a charge of -1. Neutrons are neutral. They have no charge. When it comes to mass, it's measured in AMU, which is atomic mass unit. Proton is almost 1, and neutron is also almost 1. Whereas electrons are extremely light. Another way to write this is 1/1837. So essentially what that means is electrons are extremely light, and the mass of the atom comes from the nucleus, comes from the protons and the neutrons. The next thing we want to discuss is isotopes. So what are isotopes of elements? So isotopes are basically atoms with the same number of protons. But different number of neutrons. So as you can see, the neutrons differ in all of them. So all of those are carbon, but they have different number of neutrons. And each one of these isotopes of carbon would have different abundances in nature. And there's a way to work out what your average atomic mass would be. So this is the formula that you need to remember for average atomic mass. So MR equals isotopic mass times abundance divided by 100. So 35 has an abundance of 75.8%, and Cl37 has an abundance of 24.2%. So we can use this to calculate the average atomic mass of chlorine. So what would you do? The formula is the same. So we said average atomic mass. Just gonna make this a bit smaller. So average atomic mass, or MR, equals your abundance. So in this case, say for Cl35, the abundance is 75.8. So your abundance times your atomic mass, so this is 35, plus for the second one, so the same thing, the abundance times the atomic mass, and this is going to be divided by 100. You can also choose to convert the abundance from the start to a fraction. So this would become 0.758. So then you would need to put the divided by 100. Okay, so once you compute that, that's going to come up to 35.45, something like that. And that is exactly what you see in the periodic table. Let's see another example. So here we have used the data on the table below to calculate the average mass of argon. So argon has 3 isotopes. He has 36, 38, and 40, right? The abundance are given for all 3 of them, and so are the masses. So we'll do the exact same thing that we did before. So we're just going to say average atomic mass equals what? So we're going to multiply the abundance, so respectively for each one, right? So we're going to have the abundance, this is 0.334, times its atomic mass, so this is 35.978, plus, so 0.063 times 37.963, plus we have 99.604 multiplied by 39.962, and this whole thing is going to be divided by 100. And so when you compute that, your value will come to about 39.94, and that is exactly what you would also see in the periodic table. Let's see another example on the same. This is slightly different. So here they've given you the atomic mass, but they want you to calculate the relative abundance. So this is unknown for both of them, right? Now these kind of questions where both the relative abundance is unknown can only be given when you have 2 isotopes, and I'll show you why. Because if I have this one, if I say assume this one as X, the other one would be 100 minus X, right? Because both of them, when you add them up, their abundance is going to equal 100%. Okay, so we can just use that and calculate. You could have also, if you were using fractions, then this would have become X, obviously this is X, and this would be 1 minus X. When I say fraction is when you divide your percentage by 100. So which is why I would say that both of them would equal 1, right? The addition of them, the abundance added up together, because it's 100 divided by 100, like that. So anyhow, I like to stick with the 100 minus X, and now you can set up an equation, right? Because RAM, which is basically a relative atomic mass, is basically equal to the isotopic abundance times your mass, your isotopic mass, divided by 100, remember? Now you can only have one unknown, so where do I get this? You can get it from the periodic table. So when you look up the periodic table, you will find that boron has an atomic mass of 10.811, and this is what we're going to use. Okay, so we're ready now. So the first isotope is B10. So its abundance is X. The mass is 10.0129. So we're going to say 10.0129 times X plus The other one is 11.0093 times x, right? The whole thing divided by 100, and this is going to equal to 10.811. So when you solve for x, you will get about 20% or 19.99%, something like that. And so if x for B10, so if the abundance of B10 is 20%, then the abundance of B11 is going to be what? 100 minus this value, right? Which is going to be 80. So that is 80%. And that's it. So now we're going to be discussing different aspects of the periodic table, right? What is the periodic table? How are the elements even arranged in the periodic table? What are the features and things like that? So how are elements arranged in the periodic table? They are arranged according to their increasing atomic number. So that is the number of protons, right? So you have 118 elements, and all of them, as you see from left to right, arranged in increasing order of their atomic number. Now, rows in a periodic table are called period. So the rows are called periods, and the columns, yes, the columns are called groups, right? So we have periods and we have groups.